All right. Thank you, everyone, for joining here. So today, my name is Ankit. Today, we will be talking about merge strategies at scale. And thanks for joining. I know I'm the only one who's standing between you and the karaoke in the evening today. So bear with me. We'll try to finish on time. Let me just start here. So a little bit about my background. I'm a co-founder of a new startup we call Aviator. It's aviator.co. You can check it out. We are building developer workflow automation platform, so essentially helping developers automate some of their workflows. Previously, I worked as an engineer in companies like Google and Adobe, where I've built a lot of infrastructure. And then I've worked in startups, including Shippo, HomeJoy, and Sunshine, where I've essentially helped build a lot of internal tools and help scale the engineering in those companies. So you can also find me on Twitter at AnkitXG on top right. Don't have a lot of followers, so don't care as much. But yeah, generally, I'm very passionate about helping developers be more productive. So this conversation is going to be just talking about some of the strategies some other companies use, as well as some things that we have also built ourselves to help some of the large engineering teams. But I think the first question many people may be asking is merging, how hard can it be, right? There's this big green button, you press that, why do you need to even have a talk about that? So I think one way to actually reframe this, or before even we reframe this, one thing we need to understand is differences between different repositories. And even before we go a lot into those details, I'll probably not spend a lot of time here. There was a talk in the morning by Jeff who was talking about monorepos. I know it's still a debated topic, but at least it's worth understanding the differences before we go into a lot of details about what problems we are trying to solve. So to give you some overview, monorepos, they're easier to manage dependencies because all of the things are in one place. It's easier to refactor changes, cross-project. Everyone can collaborate together. If you have vulnerabilities, everyone is it's easier to manage those vulnerabilities as well because everyone is using the same libraries. It's standardized tooling across your entire company. It's not just every team has their own tooling infrastructure, and code sharing becomes a lot easier. But there are advantages of using poly-repos as well. So some of the ones I've mentioned is your CI/CD systems are very independent and easier to manage, easier to build. Pipelines you can very easily build as well. And if there are build failures, typically they're very much localized. And the last point will give you a little bit more sense of where I'm going with it. So actually, I may have skipped one slide. No, actually, we'll come to it. So I think, yeah, this is the one, right? So we talk about one way to think about why merging is a problem is to think about how often your mainline build fails. How many people here have no mainline builds fail ever, right? So you have your CI systems, but the question here is is that CI system enough? Is that foolproof that your mainline is never failing? There are many different reasons why these change, your mainline can fail even though you have your CI systems. Some of the reasons I've explained here are stale dependencies. For instance, you're running CI on actually a piece of code which is using a very stale version of your mainline, and then you're modifying changes on it. You can have implicit conflicts where two people are working on the same code base and then trying to merge at the same time, where you can have conflicts with each other, where your your CI may pass, but your build may still fail. And this is something we'll discuss more in detail. And then there are other issues infrastructure issues where your infrastructure is unreliable. You may get timeouts. You have dependencies on third party. You have dependencies internally, or there are race conditions within your system. And then there could be maybe tests are written not written efficiently, where there are shared state flaky tests because of which your builds can fail too. So for this conversation, we will focus more on stale dependencies and implicit conflicts and explain more why merging can be challenging at scale. So to see a little bit more understand the problem, imagine there are two different pull requests. One was branched out of both of them have branched out of two different points. And both of them are actually passing your CI independently. But eventually, when you merge those changes together, it's possible that they actually will cause a build failure. So this happens very commonly, especially if you're working in a monorepo where there are many people working on the same code base. you may modify one part of one part of that change, and like somebody else will modify something else, and that can cause build failures eventually when both of them are trying to merge at the same time, or like around the same time. So why is build failure something we should be worried about? So impact of build failures can cause significant impact on developer productivity. If you look at it, like as your team sizes increase, the number of build failures also keep on increasing. Kind of, if you have like over 50, 60 developers in your organization, you will start seeing a lot more build failures happening in your mainline. And then eventually what will happen is people will set up like build police. Oh, builds failed. Now kind of like somebody needs to figure out like who's going to debug this. And they'll be like, somebody needs to roll back. Like, do we roll back like to the last green build? Do we need to like roll forward? So there's always all of those conversations. And now it's like until the builds are green, now you cannot even deploy, right? So if you're relying heavily on continuous deployments, now you're kind of like your pipeline gets stuck. And there could be like chain reactions where now people have possibly branched off of a failing mainline. That means like their changes and their PR is also going to fail. So all of those things can cascade. And eventually, like similar to like compiling, there could be like scenarios where developers are just waiting for the builds to be green before they can do anything else, right? So they might be just like stuck playing games. So I think that's one perspective, and like I wanted to explain you the problem around like why build failures and merging is a problem even with current systems that exist. So then what's the solution? So there are like some solutions that exist today for merge automation. So there's actually a concept called merge queue that GitHub has also recently announced. It's in beta. GitLab has a solution called merge train, and there's open source products like Boars, which actually also provide some of these capabilities. We'll go over some of these details and explain you kind of like how some of these things work. For simplicity, all of these merge automations, for the rest of our conversation, we will consider them as kind of like, I'll use them in the same way as like merge queues. So we'll talk about like different merging capabilities at scale. So let's talk about first a very simple version of merge queue. So what happens is, let's say you have a pull request, which was branched out of this point, and it's ready to merge. So instead of like merging manually, like kind of like pressing that green button, you can actually like just tell a merge system that it's ready to merge. What that system should do is actually it should pull the latest main line from your from the main line and then run the CI again. What we are doing at this point is we are validating your changes with the most recent main, and we are ensuring that you don't have like stale dependencies or dependencies on something else. So once this passes, you will eventually merge the change. So essentially, the merge automation is pulling these changes from the master mainline and then merging it back after validating the CI. Now, during that time, if you get another pull request to be merged, you will do the same thing, but now you're going to wait for the first pull request to actually complete and merge before picking up the second one, because then it's going to take the changes of the second one. So now you're serially merging these changes, and that's why it's called merge queue, which essentially ensures that you're always validating on the most recent changes. So that's essentially the basic concept of simple merge queue. And it's going to just validate and merge as well, the same way, right? So now if you have a very small team, let's say you have a team which merges like 10 PRs a day, your CI roughly takes about 30 minutes, which is not ideal, but it seems like a little bit more industry standard these days. We're talking about a merge time of about 5 hours. And your total number of CI runs will be 50. But, I mean, this sounds still reasonable. But if you have a team of, let's say, 100 developers, or like you're merging 100 changes a day, we're looking at like every day we need 50 hours to be able to merge changes to guarantee that your builds are always green. So obviously, this is not realistic. Then you would ask, how can we do this better? So to do this better, one of the things that Boards-like system, the open source solution I mentioned, what they do is you can actually like combine the changes together. So instead of like running validation on all changes, you essentially say, I'm going to wait for, let's say in this case, 4 PRs. Once there are 4 PRs, I'm going to consider them as like one chunk of change, pull the latest main line, and run the validation. Once the validation passes, I'm going to merge that change again. Now, what happens in case of there's a failure? So in case of failure, now you need to bisect. You need to kind of like break these changes down into 2 parts to essentially like identify which of those PRs actually caused the failure. Eventually, you'll be able to merge one of them, and the second one will fail. if in this case the second one fails, you will bisect it further. Depending on your batch sizes, it may have like almost like a binary search to identify the failing change. Now what that means for the results we saw earlier, right? For sake of simplicity, in this case, I'm going to just go over like you're merging 100 PRs a day, because we understand at least if you're only merging 10 PRs a day, it's like you can solve with simple solution. So in this case, if you're doing a batch size of 4, in best case scenario, we're still looking at 12.5 hours to merge all of those changes consistently with 25 CI runs. So we've reduced the CIs by a fourth. And a median case we are considering is like, let's say there are 10% failure rates, in which case the total merge time, roughly depending on how the failures are distributed, will be about 24 hours. So it's getting there. Like if you have exactly 100 changes, you may be able to merge all of them in the entire day, but like it's still unrealistic to expect that you'll be able to, like you would want to merge changes that takes 24 hours to hit the production. And the total CI runs are about 48, which is about half of what you were running before. So then, can we do this better? One way, so here's kind of like where it gets interesting. I want you to reimagine merges. Like the way we think about merges is there's a main line, there's a trunk where you're merging changes. So instead of thinking of like, there are PRs that you're merging in mainline, I want you to think about this as like parallel universes. So parallel universes is as if there is not like a single mainline, but there's like possibility of very many different future mainlines. And you're essentially now defining that one of those mainlines will become eventual future. So what that looks like is essentially, instead of having a single mainline, now you think of mainline as essentially like a series of commits, and you're essentially defining what the future, like you're essentially trying to predict what the next future looks like. So kind of like it already gives you a little bit of sense of where I'm going with it. So let's say your mainline is here, which is like this commit, and you get like a new PR which is now ready to merge. So instead of merging it in main, you actually merge it in another branch. We call it just main alt as an alternate reality. And let's say there's another PR that comes in. Now you're running CI. Both of them are running in parallel. We call it the optimistic mode, in which case now you're expecting if your first PR validation passes, what I can do is I can just say mainline points to the new commit. So now we are saying this is the new mainline, and anything that goes on top of it essentially becomes part of it. And again, like the second one passes, you do the same thing. Now the advantage here is if your first one actually fails, so instead of like kind of having a broken main, now you can just like create a new commit and essentially say like now this can become the future main, right? So in some ways you're validating these changes before these changes hit mainline, and thereby keeping your builds green before it actually, because you're already validating it before it becomes main. So this is a very interesting concept, right? Like now in your best case scenario, given that you're not waiting for any CI, any kind of like CI to complete before queuing anything else, technically now you can merge all your 100 changes in less than an hour, assuming all the 100 changes came in less than an hour, because you're kind of like just running it in parallel. Now, obviously, that is the best case scenario where there is no failures. In case there are about 10% failures, this is again a little bit of estimation, but now it's 6 hours. So 6 hours is still realistic. If you think about it, like it's only for 100 changes, which we are assuming, let's say if there are 100 people each merging one change, now you can still finish it during your work hours, right? So it only takes like 6 hours to merge. And the main thing here is like the CI runs are going to increase. So instead of like 100 CI runs that you were running sequentially, now you'll probably run like 150 because now you're kind of like doing more optimistic builds. So can we do something better? So one other thing which I explained before was batching. We were doing batching in a mainline concept where if your batch fails, you don't merge it. But can we combine both of those concepts together? Can we actually do optimistic queues as well as batching in the same flow? So essentially we are saying in this case is if a batch of 3, you essentially combine them and create a commit where you're running the runs. And then in the second one, you do the same thing. You combine all of those changes together and you run another batch. The advantage here is now you're running significantly lower number of CIs than you were running before. So once it passes, you kind of like just continue fast forwarding your main line to the next commit. So in this case, total number of CI runs have significantly reduced. So instead of running 100, you're running 25. your time to merge in worst case scenario also reduces because you're kind of like, doing it in batches. And the total number of CI runs are also like 48 instead of 50. Well, I think total number of CI in batching is actually about the same. Okay, so now, can we still do it better? So kind of like you understand the concept a little bit about like how I was thinking about like parallel universes, right? So now let's kind of like take it one step forward, right? We don't need to think about a single alternate reality. Can we think about like multiple alternate realities? Can we think about like all these different commits, PRs, as creating separate commits and creating multiple different branches? So in this particular case, if there are 3 pull requests, we have created it essentially, these are 7 different commits, which represent 7 different possibilities of what mainline would look like. And these are all different combinations of when a particular change passes or fails. So obviously, like this is one of the most optimal way to reduce your time to merge. The risk it comes with is obviously that now you're running significant number of CIs than you were running before, right? You're running essentially 7 CI runs just to merge 3 pull requests. So what we can do there is we can actually like use predictive modeling to figure out like which of those chains we can actually like skip because we have lesser expectation that they would pass, or we can kind of like say like some of those possible futures may have higher predictability of passing, and we can use essentially a scoring mechanism to identify which of those we would want to pick. So in this case, for instance, we are doing lines of code is a good metric to identify whether a particular change would pass or not. So at this point, we are using linear regression to predict based on history, like how often do builds fail. You can use like types of files modified. There may be certain files which actually like cause build failures more often. If whether a test is added or removed, that can also be used to know whether a particular build will pass. And number of dependencies. If there's like a lot of dependencies being modified, it's likely that it can cause a build failure versus not. So based on that, you can kind of like for every chain, you can define a particular score. And that way you can eliminate the ones which have a like lower score. In this particular case, let's say if the cutoff was 0.5, you drop anything which was below 0.5 and only try to go with the optimistic approaches with the possibility of kind of like using the same fallbacks that we were using in other systems. So it's sort of like a mix of what I explained before with optimistic queues, while in this case, it kind of like also goes with like multiple possibilities. All right, so can we still do better? So now we are kind of like getting a lot more into weeds of like how other possible scenarios we can run and like what called optimizations we can do to reduce your build times or like to reduce your time to merge. One way to think about it is multi-queue, especially if you're working in a monorepo. Not every change depends on every other change. So let's say if you have like a system like Bazel, which helps you identify what all targets were affected by a particular change, can we actually like almost build a table structure like this, where every change, every PR has a particular target that has been affected. So if we know that like there are like in a monorepo that like essentially you have a front-end change, you have a back-end change, they may not depend on each other, can we actually like run them in parallel as multi-queues? So if you have a structure like this, let's say there are targets A, B, C, and D, and there are like these 9 pull requests, how do you think about like defining the queues? So we can dynamically define queues as like first queue will run like 1, 6, 8, and 9 because that's affecting target A. Second queue will run 2 and 4, which is affecting target B and C. Third queue will run 2, 5, 6 because 2, 5, now if you see like PR2 is actually part of 2 different queues. And that's because like PR2 actually depends both on B and C. And fourth queue actually is only D because there's only one PR there. So what you're doing here essentially is now avoiding having to kind of like run them sequentially and kind of like doing them in parallel, thereby also reducing the number of queues and number of builds you have to run. To kind of like just give you a little bit more example, let's say if you have like backend and frontend as 2 different dependencies, we can actually like define these optimistic queues as 2 different queues which are completely independent but merging in the same code base. This is still guaranteeing that you're actually merging the code and keeping your builds green, even though they are actually like representing two different queues and two different states. So now, can we do something better? So I'm going to just leave these as like some further optimizations we can do. This is something which we have like thought about, like read about, but like we haven't implemented it. But like some things we can do is we can reorder certain changes. So essentially the ones which we know are higher priority or possibility of like merging, having build successful, we will merge them first before we merge the other ones. We can fail fast, where essentially we can reorder the test itself. We run the tests which are more likely to fail up early so that like your builds essentially, as soon as we know their builds have failed, you can kind of like switch over and like start afresh. You can split the test execution. This is something which many companies do, where you can run some tests which fail often before it merges, and then you run the smoke test after they merge. This doesn't guarantee build failures. Like, this doesn't guarantee like green builds, but it at least like reduces your time to merge. Okay. So far we talked about monorepo because this is kind of like where a lot of the challenges I explained come in. But it's at least worth like talking a little bit about like how these systems look like in poly-repo. So the challenges for merging are very different when we look in poly-repo. Let's take this example. A poly-repo is essentially like every project, every dependency in some ways is different. So if you have like 4 different repositories, one is API, one is web, one is iOS and Android, and you're kind of like merging, let's say you're modifying an API. This API essentially now also has to modify your web because this web is going to call the same API. You have to modify iOS because iOS is also going to call this API, and so on in Android. Now, if you have like, this is just a random example, but like if you have this kind of a scenario where, in this case, it's not like, even though they're independent changes, they sort of like still depend on each other in the way that I would ideally want to actually merge all of them together. Right? So if you have a scenario like this, where let's say all three of these changes pass, but the 4th one failed, now you have actually merged 3 changes, which technically all 4 are dependent on each other that they should go together. Right? So how do you solve this? So we have like built this system where we understand dependencies of different pull requests. When I say understand, it's like explicitly defined. But if you're able to explicitly define that, oh, like my PR in iOS, Android, and web actually depends on the PR in API, now we can actually run the system where we validate like whether all the PRs can merge together and they're considered as an atomic unit. Now in this case, like either you merge everything together while keeping all your builds consistent, or you don't merge anything at all. Right? So this is how you're kind of like building this consistency in a poly-repo system. So now you can use the same concept also in a monorepo system. You can actually like use the same dependency model and say like actually like PR2 and 3, although they are 2 different pull requests, they actually are dependent on each other. If the first pull request doesn't merge in, I don't want to merge the second one as well. So this is kind of like also a system you can use in stack PR case. You can also use it like independently, where you're essentially like saying multiple different changes are like atomically same, or like they're together. So kind of like this was some of the examples I wanted to share about like how we do merging. A little bit glance at like other things that we do at Aviator. So obviously, like there were a lot of conversations around flaky test. It's not just like we help identify flaky tests. Other things we do is like we help automatically, like if you use, for instance, PyTest, you can install a plugin which helps like automatically rerun those flaky tests, and you can kind of like from a central place configure like how often you rerun those things. We also generate these reports where we actually like show you a suppressed, like essentially suppress the flaky test that you can use to validate whether your changes are passing. And this ties in really well with like our merge validations. And we have like a API, or sorry, a CLI that you can install to manage your stack PRs. So if you have like multiple PRs running small changes, you can actually like sync all of them together. So if you have like, for instance, you introduce a commit in your base stack PR, you can actually like just use AV stack sync. This syncs all those commits to all your subsequent stacked PRs, as well as you can kind of like identify how you like merge all of those things together. So you can use AV stack merge, which will actually like help you merge all of those things together. And that's about it. So these are some of the references. Do check out. Obviously, if you are not familiar with merge queues, I would encourage you to even like check out GitHub merge queue, or like if you use GitLab, there's merge train. And if you are interested, check out aviator.co. This is a product you can sign up for free as well. And this is my email. And if you have any questions, let me know. Drop me an email, drop me a note on Twitter, or I'm happy to take any questions here. So thank you. Thanks for coming. Any questions here? Or I can also take it later. Yes?
In one of your last slides, you were talking about the poly-repos, and yeah, that one. So you're saying you can do it as an atomic unit, but isn't one of the benefits of having a poly-repo is that you can move independently?
So you
Android would then be blocking the other three.
Correct. So I think the example here is like essentially scenarios where, so one of the reasons, like it kind of like boils down to like polyrepos generally have certain library, like let's say if you're modifying a certain library, and that library has backward incompatibility. And now if you're using that library method in a different repository, you will have to kind of like modify both of those things together. So in some ways, what I'm trying to explain here is there are cases in polyrepos where you may have a dependency on some other repository, right? So in this case, like the example I was giving with API is like, these are the APIs you have to also call from iOS. These are the APIs you have to call from Android. These are the same APIs you have to call from front end. So if you're modifying the API itself, that essentially means you'll have to modify it everywhere else. So our system is guaranteeing at this point that these are atomic units, and either we are merging all of them together while keeping it consistent, or we are not merging any of them at all, right? So it's not going to be useful in every scenario. It's only going to be useful when there are dependencies across different repositories, right? So like essentially it's a place where somewhat of a limitations in polyrepos where it may actually break if you're modifying a version in a polyrepo, like kind of like or if you have like a dependency in a polyrepo elsewhere. Cool. All right. Yes?
In an instance where you have two PRs that have merge conflicts with each other, but not with the main branch.
Yeah.
I guess how do you kind of handle, is it do you queue in kind of an order of like, oh, this one was first, this goes in first, and then we'll have to fix those conflicts?
Yeah, I mean, I think in some ways, like most of these systems are able to capture that. So the question was like, how do you identify merge conflicts in two different pull requests that may not have merge conflict with the main line, right? That's kind of like some of the main like problems we are trying to solve here is like we call these implicit conflicts, where you may or like your bills may pass independently, but they fail together. In your case, you're explaining kind of like your PRs independently or like not having conflicts, but have conflicts together. So any kind of system, if you let's say if you try to do optimistic queue, we're kind of like pulling all the changes from your previous commits or like previous PRs and then trying to add the new PR to it. So at that point, we'll automatically identify the merge conflicts. So it will flag it and it will remove it from the queue automatically.
So I guess would you run like separate batches with like, oh, these three PRs can merge and these three, but if you start to do four, so they exist, like those don't work. You just have to kind of like.
Right, so generally the way it works is like every pull request when it's ready, people can use like either a slash command or they can use like a GitHub label or something else to identify that it's ready. So they assign the PR to this merge queue system. And in the order when they're assigning, we're essentially automatically adding it to either a batch or we are adding it to a particular queue. So at the moment when the batch is created or when that like, this optimistic branch is created, at that point itself, we are able to identify a merge conflict. So typically, like it's within like a couple of seconds of actually like tagging a PR is ready that we will identify this as a failure and report it back. Like our goal eventually is like also at helping identify like where we can actually optimize these things and even be able to identify merge conflicts before you even assign it to be merged, right? Because we already know what changes are there. We can actually even look at your open changes even while it's being reviewed that there are like other changes in the queue that make conflict with this. right? So generally, like our philosophy with Aviator has been around like how do we identify and like automate some of these developer workflows so that you don't have to like worry about many of these build frustrations. Cool. All right. Yes.
How do you usually know that the PR is ready?
So how do we know whether the PR is ready? So it's kind of like similar workflow, right? So if you go to, if I just go to our first example, which I was saying in this case, right? So I was saying like generally people will do is like press this button that it's merge, right? Merge directly. Instead of that, you can kind of like either add a slash command or kind of like it's manually triggered. So you can kind of like do slash Aviator ready, or you can kind of like attach a GitHub label if you're using GitHub. And similarly, like there are other ways to do it in Bitbucket or GitLab. But essentially, it's as a developer, adding it to queue is same behavior as like, it's kind of like the same mindset as like merging it directly. So instead of merging it directly, you're essentially saying is like run these pre-merge commits or like pre-merge validations before you merge it. Right? So in some ways, they're saying like just assign it to this merge queue system. Mm-hmm.
For example, if someone merged this manually and you already run a couple of queues,
Yeah.
what do you do? They run again?
I mean, so yeah, I mean, there are like different ways through which you can, so the question is whether if somebody merges any of these PRs manually, what happens? So there are like definitely like configurations you can set up, like which is what we have helped many teams with, so that they can actually like restrict people from directly merging. So one way to do that is like we can actually like define a special status check, which is like if the status check is not validated, you will not merge it. So that status check is like a separate status check that we only validate before we merge it ourselves. So in some ways, it's kind of like this can very easily be done with using branch protection rules in GitHub or like or any other system. Right? So as long as you're using a Git-based system, like all of these workflows should be able to work. All right. And thank you very much. Have a good day.